Here is a timely news story. Coronavirus testing. What is a false positive? It's by the presenters of More or Less on BBC Radio 4, a wonderful programme which will really teach you what it means to be a data scientist. There's so much credulous reporting around based on latest figures show this, that or the other, and barely any journalists understand what it means to evaluate claims made about data. On More or Less, they look into the data behind the news stories and ask if it really says what the headlines say it says. It's been a fantastic resource throughout the COVID pandemic. This is a news story explaining what a false positive is. You've learnt about them already. You've already come across Bayes' rule and used it in its canonical application to reason about medical diagnostic tests. These are the questions you can use it to answer. What is the probability you truly have COVID, given that a diagnostic test came back positive? Also, what's the probability you actually do have it if the test came back negative? The way to think about all the possible outcomes is by drawing up a table like this. There are 4 possible cases. You might have COVID and the test comes back positive, or you might not have COVID and the test still comes back positive, and so on. This is called the confusion matrix, and it's a very good name because I get confused every time I look at it. I can never keep straight in my head what words like sensitivity and false negative and specificity mean. Now, the only way I can understand what's going on is by writing out a proper probability model. Here's the probability model behind the confusion matrix idea. First, generate x, a Bernoulli random variable. Let x equal 1 mean I have COVID, and x equals 0 mean I don't have COVID. In other words, x is the indicator of whether or not I have COVID. Next, generate y, another Bernoulli random variable. Y will be the indicator of whether or not I test positive. The distribution of y depends on x. If x says I have COVID, then y is very likely to be 1. But it's not 100% certain because the test isn't perfect. And if x says I don't have COVID, then y is very likely to be 0, but again, it's not 100% certain. These numbers 0.94 and 0.01 describe how good the test is. Now, let's rephrase our question in terms of these random variables x and y. The first question is asking for the probability I have COVID, i.e. that x equals 1, conditional on seeing y equals 1. Bayes' rule tells us a formula for this probability, and we can read off the numbers we need here from the probability model. Okay, so that's Bayes' rule for a very simple probability model with 2 binary random variables. I spelt it all out like this, writing out this probability model even though you likely already know Bayes' rule, because next I want to look at continuous random variables, and this is where things get tricky. Here's an example. Here are 2 slight variations of the question. In the first variation, I want to know what's the probability I have COVID for a given level of virus in a PCR test. Here the test result y is a continuous random variable. It's the amount of virus. In the next variation, I want to know what's the probability I have a certain level of Alzheimer's disease given my score on a psychometric test. Here, the underlying condition x, the amount of neurodegeneration, is continuous. Let's just blithely go ahead and write out Bayes' rule for these 2 variations. So, what's the issue? Pause the video and see if you can spot what's wrong with these equations. When you're ready, press play. In the first variation, y is a continuous random variable, so the probability that y takes any particular value is 0. So this equation is 0 divided by 0, which is not very helpful. The other variation is even weirder. Look closely at the conditional probability here, probability that y equals 22 given that big X equals little x. Here x is a continuous random variable, so the event we're conditioning on has probability 0. How do we even define conditional probability when we're conditioning on something that never happens? Sherlock Holmes said, "Whenever you exclude the impossible, whatever remains, no matter how improbable, must be the truth." Here, we're assuming the impossible. Well, to be precise, it's impossible in the sense of having 0 probability, which is technically not quite the same thing as impossible, and it's this technicality that makes everything work. Okay, this has been a very long-winded introduction to get you used to the idea that there's something tricky and interesting about Bayes' rule. You've learnt Bayes' rule already in an elementary probability course, but now we're going to take it apart and relearn it so we know what it really means. This is where we're heading to, the reformulated version of Bayes' rule for random variables. Just read it to yourself. First thing, I've written everything in likelihood notation. The first goal of this video is to get you used to this sort of notation so that all the terms here become second nature for you. Next thing, we're going to dive deep into the meaning of these terms. A likelihood conditioned on an event that might have probability 0. We're going to interpret this conditional likelihood in a completely new way to what you learnt in elementary probability. To get going, I'm going to start with a simple probability model with discrete random variables. Discrete random variables are nice because nothing goes wrong with them, and everything that we might write down intuitively turns out to be correct. That's actually a double-edged sword, because if we only ever work with discrete random variables, we never think hard about what's really going on. So I'm going to work through an example with discrete random variables, but put it under the microscope so that what we do in the discrete world we can transpose to the continuous world. Here's the example that we'll look at. This code generates a random integer x, and then based on the value of x it generates another random integer y. Here I've plotted the joint probability mass function, or PMF, of the pair x, y, which in our language we're calling joint likelihood. For discrete random variables, the likelihood PR sub x, y of little x, little y is just the joint probability of the pair, the probability that big X equals little x and big Y equals little y simultaneously. I can plot this as a 2D histogram just by taking lots of XY samples and counting up the number of times that each pair appears. Or I could do it in maths. I can split apart the joint probability using the definition of conditional probability, and then just substitute in the probability mass function for x, which is uniform, and for y given x, which is binomial. Okay, now let's talk about marginal distributions. The marginal of y is just the distribution of y on its own. We can get this from the joint PMF by using the sum rule, also known as the law of total probability. The probability that big Y takes a value little y is the sum over all the ways that this can happen, the sum over all x of the joint probability. In other words, you sum up a row of the joint likelihood plot and you get the marginal. Or you can do it with code. We're just taking our XY samples and we're throwing away the x's and counting the y's. Next, let's talk about conditionals. You know the definition of conditional probability is just the joint probability divided by the marginal probability. Here, if I want to know what's the probability that big X equals little x given that big Y equals 3, then by the definition of conditional probability, it's the probability that x equals little x and y equals 3 divided by the probability that y equals 3, i.e. the likelihood of the pair x, 3 divided by the likelihood for y of having value 3. in terms of the picture, if I want to plot this conditional probability as a function of x, which I've done in the top plot, this equation says take the whole of the y equals 3 row, scale it so it sums to 1, and the correct rescaling must be to divide by the marginal for y, because the marginal for y is the row sum. And then this gives us the probability of any specific x value conditional on y equals 3. Okay, now let me swivel around and look at what we've just done from a completely different angle. What we've produced is a probability distribution. It's a set of probabilities which sum up to 1. So it's a legitimate random variable. It has everything we'd expect a random variable to have. It has a sample space, and it can be described with code. The sample space is just the same as that for x, of course, because that's all it's possible to produce. And here's some code that we could use in this case to sample from it. Remember, we generated this entire 2D histogram by generating lots of xy pairs and just plotting the counts. So if I want to get representative samples from the y equals 3 row, I just throw away all my xy samples that don't lie on the y equals 3 row, and what I'm left with is samples of the conditional random variable. This sort of code works fine for the discrete case, where if we sample enough xy pairs, we're sure to hit y equals 3 sooner or later. But for the continuous case, we can't start with code like this. We just have to start directly with the likelihood function. So before we do that, let's summarize where we've got to. Given a pair of random variables x and y with a joint distribution, we can define a conditional random variable written big X conditional on big Y equals little y, and its likelihood is given by this formula, which simply says take a slice from the joint density and rescale it so it sums to 1. Let me stress an important point. This is a definition. We're defining a thing called conditional random variable, and we're defining it via its likelihood. This likelihood formula here isn't something we can deduce, it's a definition. There is, by the way, a slightly different notation for this conditional likelihood, which I think reads more naturally. We read this as the likelihood for big X of value little x conditional on big Y equals little y. This reads more naturally, but the way we wrote it first is more logically correct. Great, so now we're ready to transfer these ideas across to the continuous case. The big picture to remember is this: we start from the joint density plot, and once we have that, we define marginal random variables and then conditional random variables by operations that we perform on the joint density plot. Here's some code to generate a pair of continuous random variables. In this code, x is uniform in the range -1 to 1, and y is a normal random variable centered around x squared. Now, any pair of random variables has a joint probability density function, i.e. a joint likelihood, and the joint PDF is related to cumulative probabilities by the usual sort of integral. The probability of any joint event involving x and y is just the integral of the likelihood function over all pairs little x, little y inside that event. There's a rule for how to write out the joint likelihood for a probability model of this sort, where the code first generates x and then given x it generates y. The joint likelihood is just the product of an x likelihood and a y likelihood with the appropriate x parameter substituted in. And the marginal distributions are what we get by integrating over a line of the joint density plot. Here's the marginal of y, which we get by integrating over x, i.e. integrating across a horizontal line. Okay, so we've got the joint distribution, we've got the marginal distributions. Next, to define the conditional random variable. We're going to do exactly the same as we did for discrete random variables. From the joint PDF plot, we can take a slice through it Here I've taken the slice at y equals 0.6. We can rescale it to integrate to 1, and this will give us a legitimate PDF. In other words, it gives us a random variable, the conditional random variable, big X conditional on big Y equals little y. Okay, now we've got all the groundwork laid, we're finally ready to state Bayes' rule for continuous random variables. Here's a joint density plot for a pair of random variables x and y. On the left, I've taken a horizontal slice and I've rescaled it by dividing by the marginal, and this defines for me a conditional random variable, and it's defined to have this likelihood function here. On the right hand side, I've taken a vertical slice, and this gives me the conditional random variable big Y conditional on big X equals little x. If I put these two together, I end up with Bayes' rule. The horizontal slice gives me a formula for the conditional likelihood of x in terms of the joint density, and then the vertical slice gives me a formula for the joint density. Now, Bayes' rule is a mathematical theorem about two ways of slicing the joint density. But it's a pretty useless theorem unless we can figure out the terms in the equation here. Bayes' rule is useful when the question tells us the likelihood for x and the conditional likelihood for y given x. Then we can use Bayes' rule to obtain the conditional likelihood for x given y. So that's the setting where Bayes' rule is used, when there's a piece of code that first generates x and then generates y using that x value. This video has all been very wordy, and you may at this point have no clue how to actually use any of the results in practice. But that's all I wanted to cover in this video, to give you enough of a sense of what's going on that you're not scared by the notation. In the next video, we'll go through some very concrete practical worked examples with Bayes' rule, and after that you should be confident using it yourself.